Dear students, so in this class now let us discuss about the properties of a Riemann integrable. So we already know that the continuous functions are a Riemann integrable, monotonic functions are a Riemann integrable. Also we prove that if f and g are Riemann integrable, then f plus g is also Riemann integrable. Moreover, integral a to b f plus g is nothing but integral a to b f plus integral a to b g. Now, consider another result, another theorem, which is known as the positivity theorem or positivity property. The theorem states that if f of x greater than or equals 0, if f of x greater than or equals 0 on closed interval ab, then and f is bounded, then integral a to bf greater than or equals 0. So this is our requirement. If f of x greater than or equals 0 and f is bounded, then f is integrable, then integral a to bf greater than or equals 0. How to prove this one? So its proof is, come to the proof. So let m equals infimum of f of x. Infimum of f of x, where x fall in closed interval xk minus 1 xk. Similarly, let capital M equals supremum f of x for all x fall in closed interval xk minus 1 xk. Okay. Then, clearly we know that m less than or equals f of x less than or equals capital M. Agreed? That means m into b minus a less than or equals LPF less than or equals UPF less than or equals capital M into b minus a. Sure? So, consider the left inequality. That is m into b minus a less than or equals LPF. m into b minus a less than or equals LPF means here m into b minus a less than or equals LF. Why? LPF and LF. Okay. So m into b minus a less than or equals LF. m into b minus a less than or equals LF means m into b minus a, what is LF? Less than or equals integral a to bf. Why? Since f is integrable. The hypothesis is that f of x greater than or equals 0 and f is integrable on I, then L of f is same as u of f, that is same as integral a to bf. So clearly m into b minus a less than or equals integral a to bf. But what is f of x? f of x greater than or equals 0. f of x greater than or equals 0 means f of x greater than or equals 0 means infimum f of x also greater than or equals infimum of f of x greater than or equals 0. Infimum f of x greater than or equals 0 means what is infimum f of x? That is m greater than or equals 0. m greater than or equals 0 means what is m into b minus a? It is also greater than or equals 0. Why? b minus a also greater than or equals 0. So that means m into b minus a greater than or equals 0, but m into b minus a less than or equals integral a to bf. So you can combine 0 less than or equals m into b minus a less than or equals integral a to bf. So that means 0 less than or equals integral a to bf. That means integral a to bf greater than or equals 0. This is what we require here. So the theorem states that if f of x greater than or equals 0 and which is integrable on I, then integral a to bf greater than or equals 0. This property is said to be the positive property or positivity property of Riemann integrability. Agreed? Now, by using this argument, if f of x greater than or equals 0, then integral a to bf greater than or equals 0. By using this theorem, we prove another proposition. The proposition states that if f less than or equals g on if f less than or equals g on closed interval AB and which is also integrables, then integral a to b f less than or equals integral a to b g. How to prove this one? If f less than or equals g, then we have to show that integral a to b f less than or equals integral a to b. That's immediate. Why? F less than or equals g. So that means when f less than or equals g, surely g minus f greater than or equals 0. Agree. When f of x greater than or equals 0, then integral a to b f greater than or equals 0. That is the positivity property of Riemann integrability. Since g minus f greater than or equals 0, then according to this argument, we can conclude that integral a to b g minus f greater than or equals 0. Integral a to b, but we also know that integral a to b g minus f is nothing but integral a to b g minus integral a to b f, which is greater than or equals 0. So that means integral a to b f less than or equals integral a to b g. So the proposition is immediately finished. Okay, this is heavily depends upon the positivity property of the Riemann integrability. Clear? Yes. Now let us consider another result. Suppose f is integrable on I. Consider another result and the theorem. If f is integrable on I, what is I? Integrable on I. What is I? I equals closed interval AB. Then there exists a partition P such that UPF minus LPF strictly less than some epsilon. Okay. Now, modulus of and the modulus of f of x less than or equals k means it is bounded. Modulus of f of x less than or equals k. Then we have to show that modulus of integral a to bf, modulus of integral a to bf less than or equals k into b minus a. So this is an important result. If f is integrable on I, where I is closed interval AB, since f is integrable on I, we know that for any partition P of closed interval AB, UPF minus LPF strictly less than some epsilon. And f is a bounded function, means modulus of f of x less than or equals k. Then our aim is modulus of integral a to bf less than or equals k into b minus a. So its proof is also so simple. Modulus of f of x less than or equals k. Modulus of f of x less than or equals k means minus k less than or equals f of x less than or equals k. Agreed? Okay. Minus k less than or equals f of x less than or equals k for all x fall in closed interval A. So that means can be rewrite as minus k less than or equals f of x. What is f? F is integrable. Since f is integrable on I, that is small m is the supreme of f of x and capital M be the infimum of f of x, then minus k less than or equals m less than or equals capital M less than or equals k. Okay, why? Because since f is integrable, then let m be the infimum of f of x and capital M be the supreme of f of x, then clearly m less than or equals m. So we can rewrite this minus k less than or equals m less than or equals capital M less than or equals k itself. Agreed? That means minus k less than or equals, that means yes, minus k into sigma delta xk less than or equals m into sigma delta xk less than or equals capital M into sigma delta xk less than or equals k into sigma delta xk. Okay. So that means minus k into, what is sigma with respect to k delta xk? So for all x fall in closed interval AB, so for all with respect to k, sigma delta xk is nothing but b minus a. Okay. So minus k into b minus a less than or equals m into, that is less than or equals sigma with respect to k. Instead of m, you can choose mk only for the sake of argument. Sigma with respect to k, mk into delta xk less than or equals sigma with respect to k, capital M k into delta x k less than or equals k into again sigma with respect to k delta x k is nothing but k into b minus a. Agreed. So minus k into b minus a less than or equals sigma with respect to k small m k delta x k less than or equals sigma with respect to k capital M k delta x k less than or equals k into b minus a. So that means it is minus k into b minus a less than or equals, what about this one? Sigma with respect to k small m k delta x k is, yes, it is LPF. So it is LPF less than or equals, what about this one? That is UPF. UPF less than or equals k into b minus a for any partition p of closed interval AB. Agree. So that means, what is it? But what is f? Since f is an integrable function, so modulus of UPF, so since f is integrable, then for any partition p of closed AB, then mod UPF minus LPF strictly less than some epsilon. Or since f is an integrable function, then UPF equals LPF equals or UF equals LF equals integral a to bf. So it is finally minus k into b minus a less than or equals LF less than or equals UF less than or equals k into b minus a. But since f is integrable, it is already given that f is integrable, that means LF equals UF. Okay, LF equals UF, so that means LF equals UF equals integral a to bf. So from here we know that minus k into b minus a less than or equals integral a to bf less than or equals k into b minus a. So finished. That means modulus of integral a to bf less than or equals k into b minus a. That is what we require here. Okay. So when f is integrable on closed AB and modulus of f of x less than or equals k, then modulus of integral a to b f less than or equals k into b minus a. So this is our next result. Agree? Now, we also say that, already proved that when f is integrable on I, g is an integrable function, then f plus g is also integrable. Moreover, integral a to bf less than or equals integral a to bf plus, integral a to bf plus g equals integral a to bf plus integral a to b g. Equality holder. Here, now we consider an interesting result here. That is, let C fall in closed interval AB. C fall in closed interval AB means C lies in between A and B. Now, f is integrable on closed interval AB. F is integrable on closed interval AB if and only if f is integrable on closed interval AC and closed interval CB. Moreover, integral a to b f equals integral a to c f plus integral c to b f. Means f is an integrable function on closed interval AB. Suppose C is an intermediate point of A and B. C lies in between A and B. If f is integrable on closed AB, then f is integrable on closed AC and f is integrable on closed CB. Vice versa, if f is integrable on closed AC and f is integrable on closed CB, then f is integrable on the entire interval closed AB. Then the second part, integral a to b f is integral a to cf plus integral c to b f. That is simple consequence of these arguments. How to prove the first part? C is in closed AB and f is suppose that f is integrable on both the closed AC and closed CB. That's the first argument. First suppose that f is integrable on closed interval AC and on closed interval CB. F is integrable on closed interval AC means for any partition P1 of closed interval AC, what do you get? U P1F minus L P1F, U P1F minus L P1F strictly less than some epsilon by 2. Okay. Again, for any partition P2 of closed interval CB, then since f is integrable on closed interval CB, for any partition P2 of closed CB, then U P2 f minus L P2 f strictly less than some epsilon by 2. Okay. Let P equals P1 union P2. Means P1, P with a refinement of both of this P1 and P2. P is finer than both P1 and P2. Then surely since P1 and P2 are partitions of closed AB and closed AC and closed CB respectively, hence P be the partition of closed interval AB itself. What is actually P? P1 union P2, which is finer than both of P1 and P2, means it acts as a refinement of this P1 and P2. Since P1 is a partition of closed AC and P2 be a partition of closed CB, then by according to this construction, we can immediately conclude that this P is nothing but a partition of closed interval AB. Clear? Now what is UPF? So what is UPF? Since P is P1 union P2, then UPF is nothing but it is U P1F plus U P2F. Okay? Since P is P1 union P2. But what is UP1F? It is strictly less than LP1F plus epsilon by 2 from this argument. So it is strictly less than LP1F plus epsilon by 2 plus what is UP2F? From here it is LP2F plus epsilon by 2. LP2F plus epsilon by 2. So that means that equals LP1F plus LP2F plus epsilon. So UPF less than or equals LP1F plus LP2F plus epsilon. What is LP1F? LP1F plus LP2F is nothing but LPF. Why? Because P is P1 union P2. Also we know that is LPF equals LP1F plus LP2F. Okay. So it is equals some LPF plus epsilon. Since epsilon being arbitrary, then we know that so it is UPF less than or equals LPF. UPF strictly less than LPF plus epsilon. That means UPF, since epsilon being arbitrary, UPF less than or equals LPF. That means or UPF minus LPF strictly less than whatever may be from here. UPF minus LPF strictly less than epsilon. UPF minus LPF strictly less than epsilon means f is integrable on I for the partition P of closed interval AB. So the first part is finished. When f is integrable on both of the interval closed AC and closed CB, then here we prove that f is integrable on closed interval AB. So first part is finished. Come to the reverse inclusion. Reversely, next suppose that f is integrable on closed interval AB. Now let's suppose that f is integrable on reverse inclusion. F is integrable on closed interval AB. Now to show that this f is integrable on closed interval AC and f is integrable on closed interval CB. That is the reverse inclusion. So since f is integrable on closed interval AB, so for any partition P of closed interval AB, by the Riemann criterion, it is UPF minus LPF strictly less than some epsilon. Okay, for any partition P of closed interval AB. Let P epsilon equals P union singleton set C. P union singleton set C. What is P? P be the partition of closed AB. What is P epsilon? P epsilon is setting as P union singleton set C, where C lies in between A and B. Surely this P epsilon is another partition of closed interval AB. No doubt. Moreover, this P epsilon is a refinement of P. It should be finer than P itself. Okay. So, therefore, we have UP epsilon F, UP epsilon F minus LP epsilon F strictly less than some. So epsilon. Why? because UP epsilon f minus LP epsilon f, it is less than UPF minus LPF. Why? Because P epsilon is the refinement of P. Then, but UPF minus LPF strictly less than epsilon. Thus, UP epsilon f minus LP epsilon f strictly less than epsilon. Why? Because of the choice of P epsilon. P epsilon is setting as it is nothing but the refinement of P, means it is setting as P union singleton set C. Okay. Now, so P epsilon dash, you can construct another one, P epsilon dash equals P epsilon dash equals P epsilon intersection closed interval AC. P epsilon dash is chosen as P epsilon intersection closed interval AC, and P epsilon 2 dash equals P epsilon intersection closed interval CP. P epsilon dash and P epsilon 2 dash are again resetting as one is P epsilon intersection closed AC and the other is P epsilon intersection closed CP. Okay, then clearly UP epsilon F equals, what is UP epsilon F? UP epsilon F equals UP epsilon dash F plus UP epsilon double dash F. Okay, right. Similarly, what is LP epsilon F? LP epsilon F is nothing but it is LP epsilon dash F plus LP epsilon double dash F. Here. Okay. So, therefore, this combining these two with this formula, then UPF minus LPF strictly less than epsilon means UP epsilon dash F minus LP epsilon dash F plus UP epsilon 2 dash F minus LP epsilon 2 dash F strictly less than epsilon from here. If you combine here, so you have UP epsilon dash F minus LP epsilon dash F plus UP epsilon 2 dash F minus LP epsilon 2 dash F strictly less than some epsilon. Okay. If you combine or using these two arguments in this result. Since both of these two intervals are two brackets are non-negative. So UP epsilon dash F minus LP epsilon dash F less than some epsilon by 2. This also strictly less than some epsilon by 2. Sure, because of both of these two brackets are non-negative. What about this one? That means F is integrable on this one. Means F is